Good morning, everyone. Welcome to GATE subject electronic devices. As we have seen in last classes, and we have started the semiconductor physics, and we have gone through different topics in semiconductor physics. And in last class, exactly we have learned about uh, drift current, how the drift current is existing, what type of semiconductors we have taken, and then problems related to the drift current. Now, today, let us see the topic called diffusion current, which is exactly opposite to that of drift current. So, in drift current, we have taken, we have processed two steps. Those steps are nothing but we have used the first one, we have used a uniformly doped semiconductor, and the second step is we have applied external electric field. That is E. But here in this diffusion current, let us hope the exact opposite operation of drift current, which is nothing but diffusion current. So here we need to take into consideration two steps. The two steps are like this. The first one is non-uniformly doped semiconductor is used. Non-uniformly doped semiconductor is taken, and the second point is we need to take we do not apply external electric field. So therefore external electric field is not applied. E is not applied. So these are the two important points that we need to consider before starting the diffusion current flow, which are the opposite of operation of drift current. So the first, I am taking non-uniformly doped semiconductor. As you see here, this is a non-uniformly doped semiconductor, which it may be of p-type semiconductor or it may be of n-type semiconductor. Now for better understanding, I am taking here a p-type semiconductor, a non-uniformly doped p-type semiconductor I am taking here. P-type semiconductor means majority charge carriers are holes, and minority charge carriers are electrons. So you can see here all these yellow dots are majority charge carriers, which are nothing but holes. So here, and that too, this semiconductor is non-uniformly doped. So what is non-uniformly doped concentration means? Semiconductor means. So here, if you consider 1 meter distance, more number of charge carriers are there. If you consider another meter distance, less number of charge carriers. So as you move forward, then as distance increases, the charge carrier concentration is decreased. So it is not uniformly doped. So this type of semiconductors, which are different as the distance moves from 0 to some other longer distances, then that concentration may decrease. So that type of semiconductors are called non-uniformly doped semiconductors. So this is the best example of non-uniformly doped semiconductor, and I am not applying any external electric field here, right? So now let us observe how does current flows in this type of semiconductor, which is non-uniformly doped semiconductor. So I consider here charge carriers. As you see here, there are more number of charge carriers here. So as charge carriers are lying nearby each other, what happens is they will get bombardment because they are of same charge. This is a hole which is of a positively charged. This is a hole which is a positively charged. This is a hole which is a positively charged. So they are very near to each other. If they are very near to each other, they will repel with each other. They will bombard and they will repel and they will move towards the space which is not having a concentration. That means they are moving from higher concentration to lower concentration, because they are being occupied here with the full space. So they will get bombarded with each other because they are having a same space, same positive charge. So therefore they will repel with each other and they will try to move towards the other region where the empty space is there. Here we are not applying any external electric field, and they are themselves are moving from one point to another point. Nothing external electric field is moved here, is been applied here. So therefore charge carriers, they themselves starts moving from one point to another point because of they are having same charge. So they will repel each other and tries to move from left side towards right side where the concentration gradient is very less. So they themselves are moving and the charge carrier is moving its position from one point to another point. In turn, current is flown in the device. As I told you already, a charge carrier, if it moves its position from one point to another point, shifts its position from one point to another point, changes its position from one point to another point, definitely a current is existing. That current, it may be due to holes or it may be due to electrons. But here we are using a hole, so therefore the current is existing due to holes. So therefore, hole current exists here. That hole current, due to bombardment of the charge carriers, due to repulsion of the charge carriers, and they are moving from higher concentration to lower concentration. So therefore, that current is nothing but called as a diffusion current. Diffusion current. So the current which is existing due to bombardment of the charge carriers, due to diffusion of charge carriers from one point to another point. So this current is called a diffusion current. Diffusion current. And as you see, if you take x-axis as distance x, and this is the y-axis as concentration, we consider as a concentration gradient, concentration as p, because it's number of holes. So therefore here I take its x is equal to 0. As you go like this, distance goes on increases, x is been going on increasing. So if x is increasing, what happens is, I can say that this is x and this is the concentration of holes p. So therefore at x equal to 0, there is a large concentration, and I can say this one is P naught. At x equal to 0, the concentration is P naught. So as distance increases away from x equal to 0, the concentration of holes decays. The concentration of holes decays. So this decaying is called as a gradient. Decay is nothing but called as a gradient. As if you find the slope of this graph, where slope is given by, slope of the graph is given by, as you know mathematically, the slope is equal to dy by dx. Slope is equal to dy by dx. And dy, it is in y-axis. We are taking concentration in y-axis as p, in x-axis as distance. So slope is equal to dp by dx. This slope is been decaying. So what is decaying actually here? Concentration is been decaying. Decaying, the term which is nothing but a decrement. Decrement is the term, technically we can call it as a gradient. So therefore the slope can be called it as concentration gradient. Concentration gradient. Because the charge carriers are been decaying from higher concentration to lower concentration. So therefore I can call this one as the charge carriers as concentration, and the decaying is a technical name called as gradient. So concentration gradient is given by dp by dx. dp by dx. Now as current is existing here from this point to this point, current density also exists. As I told you already, current density is nothing but a current produced per unit area. That is nothing but current density. So here we are constructing the semiconductor with respect to holes. So since it is a p-type semiconductor, so current density due to holes it exists. That is current density, which is nothing but diffusion current density due to holes. Diffusion current density due to holes. So diffusion current density due to holes means current density is given by J, and due to holes means it is given by P. So therefore Jp is here directly proportional to the concentration gradient dP by dx. Concentration gradient dP by dx. So Jp is directly proportional to dP by dx. Jp is equal to E dP by dx. That is, E is called charge of the carrier, dP is called diffusion constant of holes, and dP by dx is concentration gradient. E is called charge. dP is called diffusion constant of holes. And dP by dx is called concentration gradient. So a formula exists for diffusion current density, which is nothing but Jp is equal to E dP into dP by dx. But as you know, here all holes are positively charged particles. But here in this formula, as dP by dx is a negative quantity because it's a decaying, because the concentration is been decreasing. So decrement term mathematically can be written as a negative one. So I can say that this dP by dx is a negative quantity. But here we are talking about holes. Holes are because it's a p-type semiconductor. P-type semiconductor, majority charge gases are holes. Holes are of positively charged particles. So therefore here current should be a positive one. So therefore here dP by dx is a negative quantity. In order to make sure to become current as a positive one, I am adding a negative here, minus E into dP by dx. So the decrement of dP by dx can be compensated by adding a minus 1. Minus of minus becomes plus. So therefore current density of holes is nothing but a positive quantity. So therefore here Jp is equal to minus E into dP by dx. This is what the diffusion current density due to holes which is existing in a non-uniformly doped semiconductor and without applying any external electric field. Now similarly I can take a semiconductor as n-type semiconductor, which is a non-uniformly doped and it is due to electrons. So you can write directly as Jn, which is a diffusion current density of electrons. So diffusion current density of electrons is written as, actually the same formula exists, minus E into dN into dN divided by dx. So concentration gradient is electrons and dN is diffusion constant of electrons. E is the charge of electron, but charge of the electron is negative. So already minus is present, minus of minus becomes a plus. So this is diffusion current density of electrons, where Jn is equal to plus E dN into dN by dx. dN by dx. So this is nothing but units are amperes per meter square. Here also units are amperes per meter square, or you can also take centimeter square also, right? So this is regarding diffusion current density. So there are only two differences between diffusion and drift, where the two differences are drift is a uniformly doped semiconductor, whereas diffusion is non-uniformly doped semiconductor is taken, and drift exists for applied external electric field, but diffusion exists without applying any external electric field. So these are the two differences between diffusion current and drift current. Next, let's go with the small topic which is called Einstein's relation. What is Einstein's relation? At a constant temperature, the ratio of diffusion constant to mobility is nothing but a constant. What is that constant value? What is that constant? That constant, we can write this one as the ratio at constant temperature, the ratio of diffusion constant to holes or mobility of holes, ratio of diffusion constant to electrons or mobility of electrons is a constant which is nothing but Vt. Vt is called volt equivalent temperature. Vt is called here volt equivalent temperature. Vt is called volt equivalent temperature, and it is given by Vt is equal to Kt by Q. Kt by Q, this is a formula for volt equivalent temperature. Vt is equal to Kt by Q, where K is called Boltzmann constant. K is called Boltzmann constant, and it is given by K is equal to 1.38 into 10 power minus 23 joules per degree Kelvin. Joules per degree Kelvin, and Q is the charge of charge carrier, where it's equal to 1.6 into 10 power minus 19 coulombs, and T is nothing but temperature in degree Kelvin. Temperature in degree Kelvin. So Vt is equal to, you can substitute here Boltzmann constant 1.38 into 10 power minus 23 joules per degree Kelvin into capital T is temperature, to 1.6 into 10 power minus 19 coulombs. So if you do this calculation, the value of this one becomes Vt is equal to capital T divided by 11,600 volts. This is a very, very important formula. You can remember for competitive exams, where Vt is equal to T by 11,600 volts. T is the temperature. For example, case 1, at capital T is equal to room temperature. Capital T is equal to room temperature. So what is the room temperature? 27 degrees C is the room temperature. But you need to convert into kelvins. 27 degrees C plus 273, that is equal to how much? 300 degree Kelvin. 300 degree Kelvin. So therefore, volt equivalent temperature Vt is equal to capital T is 300 divided by 11,600. So if you do it, you will get approximately 26 millivolts. 26 millivolts. 0.026, or it's also equal to approximately 0.026 volts or 26 millivolts. Similarly, if you apply for another temperature, you can change the temperature 27 degrees C or 37 degrees C. The problem may exist and ask in competitive exams like 37 degrees C, 47 degrees C or 57 degrees C. Likewise, just you can directly substitute here T by 11,600 and you can find the answer here. Okay. So this is about the Einstein's relation. Next, let's go with another topic which is called as carrier lifetime. The lifetime of a charge carrier. What is the lifetime of a charge carrier? The lifetime of a charge carrier, which is nothing but a carrier lifetime, is nothing but it is defined as the time taken by the charge carrier from generation to recombination. The time taken by the charge carrier from its generation to recombination. When it is generated, actually, when it is generated, suppose this is an electron, when it is generated, and if it is a hole, if this electron fills this hole here, then it will be recombined here. This is recombination and this is called as generation. So what is this time gap from generation to recombination? That time is called as carrier lifetime, which is nothing but tau. So the time taken from its birth to death, that is from generation to recombination, is nothing but called as carrier lifetime, which is called as tau. So therefore, the formula to find the carrier lifetime, how much it is actually, formula to calculate the carrier lifetime is tau is equal to, tau can be written as L square divided by T, L square divided by D. So that means carrier lifetime is calculated with respect to L and D, where L is called diffusion length of charge carrier, where L is called diffusion length of charge carrier. It may be, L may be diffusion length of holes, or it may be diffusion length of electrons, and D is called diffusion constant of charge carrier. Diffusion constant of charge carrier. Diffusion constant of charge carrier, where D can be taken for dP, it can be taken as dP for p-type semiconductor, which is nothing but diffusion constant of holes, and D can be taken as dN, which is nothing but for n-type semiconductor, and it is called the diffusion constant of electrons. So therefore, so you can write definitely as carrier lifetime of holes can be written as diffusion length of holes by diffusion constant of holes, or it can also be written as LP is equal to square root of tau P into dP. Tau P into dP. So units or seconds. Carrier lifetime time means it's nothing but seconds. So similarly here, tau n, diffusion carrier lifetime of electrons is given by tau n is equal to ln square divided by dn, that is equal to ln is equal to square root of tau n into dn. This is the diffusion constant of electrons. dp is the diffusion constant of holes, and ln is the diffusion length of electrons, lp is the diffusion length of holes. And likewise you can able to calculate the carrier lifetime of electrons and carrier lifetime of holes. Okay, now let us see some important problems which have been asked in competitive exams. The first one, assume electron charge q is equal to given q is equal to charge of carrier q is equal to 1.6 into 10 power minus 19 coulombs. Kt by q is given, it's equal to 25 millivolts, which is nothing but Vt. Vt is equal to Kt by q, 25 millivolts, it's been given. And electron mobility mu n is given, mobility of electrons mu n, which is nothing but 1000 meter square centimeter square per volt second. And if the concentration gradient of electrons injected into a p-type silicon sample is 1 into 10 power 21 per centimeter power 4, the magnitude of electron diffusion current density in amperes per centimeter square is dash, that is mu n, and also electrons injected into a p-type silicon sample is concentration gradient of electrons, that is dn by dx is equal to 1 into 10 power 21 per centimeter power 4, that is concentration gradient of electrons injected into a p-type, means from n-type to p-type. So therefore dn by dx is given 1 into 10 power 21 centimeter power 4. So then you need to find, required to find, what you need to find? You need to find the magnitude of electron diffusion current density, electron diffusion current density, that is Jn is equal to how much in amperes per centimeter square. Jn you need to find. So according to this formula, we have already know that just now we have seen and we have learned about diffusion current density, which is nothing but diffusion current density is given by Jn is equal to diffusion current density of electrons is given by Jn is equal to E plus E dn into dn by dx, where E is the charge of electron, dn is the diffusion constant of electrons, and then dn by dx is the concentration gradient. Next, but here dn is not given, I think dn is not given, but mu n is given. So how to find dn? But mu n is given here. So substitute here Jn is equal to E is 1.6 into 10 power minus 19 coulombs, dn is not given, and dn by dx is given 1 into 10 power 21. But how to find dn here? And also Vt is given, and dn we need to find. How to find dn? Just now we have seen volt equivalent temperature, Einstein's relation. According to Einstein's relation, what is volt equivalent temperature? Vt is equal to Kt by q, which is already given here 25 millivolts. But according to Einstein's relation, we can say that ratio of dn by mu n is equal to dp by mu p, or dn by mu n is equal to Vt, that is equal to dn we need to find. Dn is equal to mu n into Vt, that is equal to mu n is 1000 into Vt is 25 milli means 10 power minus 3. So therefore dn is equal to how much? Dn is equal to 25. So we have found from volt equivalent temperature dn is equal to 25. Then substitute here in Jn is equal to diffusion current density Jn is equal to 1.6 into 10 power minus 19 into 25 into 10 power 21. So therefore Jn is equal to 21, substitute, cancel it, so you get 1.6 into 25, you get 4000 amperes per centimeter square. 4000 amperes per centimeter square. So the magnitude of current density here is 4000. So like this, you need to find the formulas, you need to find this problem which is given in competitive exams. Next, let us see what are the other problems that have been asked in competitive exams. So this is the one of the question which been asked. The units of Q by kT or dash. A option is given V power minus 1, J by K. We already studied how to find the units of Q by kT here. How to find the units of Q by kT? What is Q by kT? We learned about volt equivalent temperature Vt, which is equal to kT by Q. Volt equivalent temperature is kT by Q. Its units are volts, or it can be written as V. But here, what is this one? It's a Q by kT. Q by kT means what? Q by kT is equal to 1 by Vt. That is equal to units are 1 by volts. That is equal to 1 by V, or it's equal to V inverse. So answer is B. It's equal to V inverse. Volt equivalent temperature units are volts, and here inverse of volt equivalent temperature, which is Q by kT. So therefore units are volt inverse. Okay, right. Next, determine the thermal voltage Vt at a temperature of 127 degrees C. How to find this type of problem? At thermal voltage Vt. I told you volt equivalent temperature. Thermal voltage is also called volt equivalent temperature. Thermal voltage is also called volt equivalent temperature. Volt equivalent temperature, which is nothing but Vt. That is equal to, the formula is kT by Q. K is Boltzmann constant, T is temperature, Q is charge of the electron, 0.6 into 10 power minus 19. Substitute all the values. Already we have got a small formula, T by 11,600. So therefore substitute T value, it is 127 degrees C. T is given 127 plus 273. That is equal to how much? 400. So T is equal to 400 divided by 11,600. So answer you get 34.5 millivolts. 34.5 millivolts. So this is what the volt equivalent temperature at 127 degrees, and you need to find, convert into kelvins, then substitute in the shortcut method, which is T by 11,600. You will get the answer as 34.5 millivolts. Okay. So thank you so much. We'll stop over here and we'll continue next class.